Hello and welcome to the Week 2 lecture for microprocessors and robotics. This week we're going to be covering binary addition, signed binary numbers, signed meaning positive and negative, 2's complement, which is related to signed numbers. We're going to talk about logic gates, their applications, and we're going to take a look at the architecture of microprocessors and microcontrollers and some more details of their components. So this graphic should look familiar. We took a look at it last week. This is on significant bits, or significant numbers, rather, as a generalization. So looking at graphic A on the left here, the most significant bit is always going to be the leftmost bit, and the least significant bit is always going to be on the right. It's going to be the rightmost bit. On the right side, we're looking at a hexadecimal number, and instead of using bits, we're looking at bytes. So the most significant byte is again on the left, the least is on the right. If we wanted, we could use different terminology, right? We could use nibbles. A nibble is 4 bits of data. That would be one hexadecimal number. So hopefully now after last week you have a firm grasp of the binary and hexadecimal number systems. Now we're going to jump into performing some additional operations with binary numbers. And the first and main thing we're going to look at this week is binary addition. So binary addition is not unlike regular addition, right? On the left we have it here, 7 plus 9 is 16. We're writing down the 6 and we're carrying the 1, right? And we just keep adding and carrying as needed. The binary addition system it works the exact same way, same principles, except we can only count up to 1, right? And then we have to go to the next binary number, which would be 2, which looks like it's written as a 10. So here we have on the right side 1 plus 1, and that equals 1, 0 in binary. So we write the 0 and we carry the 1. So you're going to be doing this a lot. This is very important to remember, and just link it together in your mind that 1 plus 1 in binary, the result is a 2, but 2 is written as 1, 0. So here's a little example of binary addition, and we'll walk through a couple more examples in a minute, but here you see we're just continuously carrying. So 1 plus 1 is equal to 1, 0. So we're going to write the 0, carry the 1. We have another 1 plus 1 that equals 2, or 1, 0, right? So we're going to write the 0 again, carry the 1. And here we have 1 plus 1 plus 1, which in the decimal system would be 3. But in binary, that's actually 1, 1. It looks like 11. It represents the number 3. So here we're going to write the 1, and we're going to carry the 1. And then 1 plus 0 is, of course, 1. So adding the two binary numbers 0, 1, 1, 1 plus 0, 1, 0, 1 equals 1, 1, 0, 0. And we'll step through a couple more examples and look at their decimal equivalents as well as kind of a check to help you ensure that you're performing the binary addition correctly. So we have two binary addition examples to take a look at in addition to what we just went over. So the first one we have is the decimal equivalent of 6 plus 5. And you should know that 0, 1, 1, 0 is how you write the number 6 in binary. And likewise, 0, 1, 0, 1 is the number 5 written in binary. So we're going to start by adding the 0 and the 1 on the rightmost side over here. And of course, that's going to be a 1. Next column, 1 plus 0 is of course 1. Now we have 1 plus 1, which remember is 2, but we write that as 1, 0 in binary. So we're going to write the 0 and we're going to carry the 1. And then we have 1 plus 0, which is going to be 1. So this addition system in binary is exactly like it is in the decimal system. You're just restarting your numbers faster, right? We don't have the numbers 0 to 9. We only have 0 and 1. So you're still carrying, you're still adding the same way. You just have to be familiar with your binary numbers in order to make sure that you're writing down and carrying the correct numbers. And we can double check this, so we know that 6 plus 5 in decimal is equal to 11. And if we look at this number here that we are left with, you should know this is 8 plus 2 plus 1, which equals 11. So that's a nice check. If you're not sure if you're adding binary correctly, add the decimal equivalents and then try to do this conversion if that's any easier for you, and that serves as a check for your work. So we'll do one more example of binary addition. Here we have the binary number 15 and the binary number 9. So we have 1 plus 1 all the way on the right. We're going to write down the 0, carry the 1. 1 plus 1 is going to be 0 again. We're going to carry the 1. And again, we have 1 and 1, so we're going to write the 0, carry the 1. And so here we have 3 ones, right? So this is 3 in decimal form, but it is 1, 1 in binary form. So we write our 1, and then this other 1 would be carried over here, and of course it would just drop straight down. So we know that 15 plus 9 is 24 in decimal. And you can do this check on the left side with this binary number that we've come up with. This is 16 all the way on the left, right? We just go up a power each time. With 2's, it's really easy. It just doubles as we go up. So we have 16 and an 8 and nothing in the remaining columns. So 16 plus 8 is 24. So that's our check. We know we've done the addition correctly. So now we can add positive binary numbers, but what about negative binary numbers, right? We have positive and negative decimals, and likewise we have positive and negative binary numbers. So what we do for this, if a number is a negative, we make the most significant bit a 1, and this is why it was important to have a refresher on our significant bits. So the most significant bit is the one all the way to the left. If the number is a positive number, that most significant bit is going to be a 0. So for example, we have this positive 5 down here, and this one is not too hard. So we want to make sure that our most significant bit is 0, and then of course we have 4 plus 1, that equals 5. So this is good. For negative 5, what we're going to do is we're going to write, you can write the number 5 as you normally would, right? 4 plus 1, but this most significant bit, we need to make a 1, and this indicates that this is a negative number. So it's important to know if you're working with regular numbers or if you're working with signed binary numbers, because this bit all the way on the left here, under my negative 5, this is not representing the number 8. So if this was a typical binary number, this would be 8 plus 4 plus 1, which would be 13. This number is not 13, right? It's negative 5. So it's important to know that you're working with a signed binary number, and your most significant bit is not representing a number. It's only representing if the following number is positive or negative. We don't add this in. So keeping that in mind, let's look at a couple examples down below. And we'll walk through and see if they're positive or negative. This should be pretty simple. So this first number here, 1001, this is going to be a negative number, right? The most significant bit is a 1. So this is actually the number negative 1. Okay, our next number here starts with a 0, so that's going to make it positive. So this number is going to be a positive 5, right? It matches our example above. All right, our next number, most significant bit is a 1, so we know it's going to be a negative binary number. And remember, we don't count this most significant bit when we're working with signed numbers. So that means we're only counting the second one here, and this is going to actually be a negative 4. All right, our last one, most significant bit is a 0, so we know that's going to be positive. So this is just a positive 1. So signed binary numbers are very useful when we need to represent a negative binary number. Where we run into trouble is where we try adding signed binary numbers. So we have our examples of positive 5 and negative 5 over here on the left. We know that these are the signed equivalents, right? We have a 1 here to indicate this is a negative. So when we look at the addition for these numbers, we should recognize that a positive 5 plus a negative 5 equals 0. They cancel each other out. However, when we add their signed binary numbers together, and I will go through this really quick. So 1 plus 1 is 0. Or I'm sorry, it's 1, 0. So we write the 0, we would carry the 1. The 1 comes down here. 1 plus 1, write the 0, carry the 1. 1 plus 1, write the 0, and then the 1 carries all the way down. So what we end up with is 1, 0, 0, 1, 0, which we can clearly see does not equal 0, the answer we should have gotten. So unfortunately, we cannot add signed binary numbers. Signed binary numbers are good for representing the number. They're fine for that. But when we have to add negative and positive binary numbers, or if a negative binary number is involved in some way in the addition, we have to do something different. That something different is what is called a 2's complement, and it's similar a little bit to our signed binary in that the most significant bit is still reserved for our sign notation. So a 0 most significant bit, that's what MSB stands for, tells you that it's a positive number, and a 1 as your most significant bit is indicating that it's a negative number. That is still valid. However, we do something a little bit to these numbers. When we have a negative binary number, we convert it to its complement. And what that means is we invert the number, so all the zeros turn to ones, all the ones turn to zeros, and then we add 1. So let's take a look and see what that looks like. So I need to represent the number -3 in 2's complement binary form. That way I can add it to something. So what we're going to do first is write out the number 3 in binary. And the most significant bit's going to be a 0 because it's a positive number, right? We'll just start with the positive version, 0, 0, 1, 1. That's the binary equivalent for 3. And so the first thing we're going to do to get it into its 2's complement form is to invert it. So again, inverting just means if it's a 0, it changes to a 1. If it was a 1, it flips to a 0. So just flip all your numbers around. So instead of 0, 0, 1, 1, we now have 1, 1, 0, 0. So that's our inversion. Our second step is to add 1. So 1, 1, 0, 0 plus 1. This is pretty easy addition. It just gets tacked on to the end here. We have 1, 1, 0, 1. And this is the 2's complement for -3. Now again, it's important to know what system you're working with, right? Just like if you are not sure if it's signed binary or unsigned binary, the numbers can represent different things. Same goes for 2's complement. So if we didn't know this was a 2's complement and we thought this was a regular binary number, we would think this was 8 plus 4 plus 1. And this would look like the number 13, and it's not, right? If we thought it was just regular signed binary, we would think that this was a negative, because we do have our most significant bit is a 1, but then we would think we would still have a 4 and a 1, which would be 5, which is also incorrect. So for 2's complement, we have to know what we're working with in order to know what the actual true number is. So just bear that in mind as you go. Pay attention to what number systems that you're using and what version. Is it typical binary number? Is it signed? Or is it a 2's complement? Always be very cognizant of that when we're working with these numbers. Now we're going to walk through 3 different examples of turning binary numbers into their 2's complement version. So this you can actually do starting with either a signed binary number or an unsigned binary number. So we'll look at signed binary first. So -1 we would write as 1001, right? Our most significant bit is representing that this is a negative. And so the first thing we're going to do is invert these numbers. So all of our zeros turn to ones, all of our ones to zeros. The only difference between using signed binary and unsigned binary when you're converting is what happens to that most significant bit. So if you start out with a signed binary number, you're going to maintain that signed bit. So this first one here does not get inverted. Only if you're working with signed binary. Keep this to indicate that it's a negative. Otherwise, everything else flips. And then we're just going to add a 1. So this here is the 2's complement version. this represents -1. So now we'll go to -7, and in signed binary, this is 1111, right? So this first bit represents that it's a negative, and then we have 4 plus 2 plus 1 equals 7. So this is -7 in signed binary. And again, this is where it's really important to know what state you're working in, or what part of the number system, because in signed binary, this -7 looks like the 2's complement version of -1. So just know which system you're working with. So again, when we start with a signed binary number, we leave that most significant bit alone, but everything else flips or inverts. So all of the ones turn to zeros, and then we simply add 1. So this is the 2's complement representing -7. Now going on to -4, our most significant bit represents a negative. This bit right here represents 4. So the first thing we do is invert. And we're working with signed binary, so I'll say it again. This first bit, it stays as is to represent the negative. Leave that one alone. Invert everything else. And then we're just going to add 1. So be very careful when you're adding. Write it out on paper if you have to. But when we add 1 to 1011, we get 1100. And that's just because of the carrying, right? So our next number after what looks like 11 in binary, we have to go to what looks like 100. Okay, so that's converting signed binary into its 2's complement. We can also start with an unsigned binary number. It is just very slightly different. So the unsigned binary version, we would just have the number 1, not worry about the negative yet. But the difference is you invert everything. So when we started with signed binary, we kept that most significant bit, and we carried it all the way down. When you're using unsigned binary, you don't have to do any of that. You just start with a regular old, what looks like a +1, and then you flip all of it. And then we add 1. And you can see we still get the same answer. So you can start from either one of these and convert to 2's complement. And we can see the same thing with -7. This number right here looks like +7, but since we're using unsigned binary, we just flip everything and add 1, and we get the same answer as we did up here. Same thing for -4. We're not using our most significant bit to represent that it's a negative yet. We're just writing out the binary number 4, which means we flip everything. Even the most significant bit, we flip, and then we add 1. And again, these numbers are equal. So you can start with either signed or unsigned. You just have to know if you need to carry that most significant bit down and keep it the same, or if you need to flip that as well. So just bear that in mind. So when you're working with 2's complement, it might be confusing as to what number is actually being represented, right? In the previous slide, we had the 2's complement representing -1 look just like the signed version of -7. So if you have a number in its 2's complement version, how do we find out what it really is? How do we get it back into our typical binary version? So there's 2 ways we can do this. The first method is a little bit more difficult, but it's also a little bit more common sense, I think. So to get to 2's complement, we are inverting and we're adding 1, right? So common sense says that we just do the opposite to get back to the original number, which would be subtracting 1 and inverting again. So I have this number down here, 1001. We know this is a 2's complement number. So let's perform these steps on it, and we'll see what number we actually have. So the first thing we're going to do is subtract 1. This 1 drops off here. We just have 1000. And then we invert. We flip everything. And this is going to be the binary version of this number. And this is just a -7. So how do we know that it's -7? We look at the most significant bit, right? This should signify that this is going to be a negative number. And so we're converting 2's complement into binary, into unsigned binary. So we just have to keep it in our minds that the most significant bit is either going to indicate that the number is positive or negative. So we know that these equal 7, and we started out with a 1 as our most significant bit, so it's going to be a negative number. So the 2's complement number 1001 is equal to the unsigned binary number -7. A second method to converting a 2's complement number back to its unsigned binary form is to actually perform the exact same actions that we did to get the 2's complement. So to get the 2's complement, we invert and add 1. To switch it back, we can actually do the exact same thing, just invert and add 1 again. So I have the same number here, 1001. So this is our 2's complement version. And again, we need to take note that this most significant bit indicates that this is a negative number. So we invert, flip everything, add 1, and we end up with 7. And we have to add the negative back, right? We have to keep in our minds that this most significant bit indicates this is a negative number, so -7. So you can see we got the same result. And you can use whichever method is easiest for you. I think it's easier to remember that you always just invert and add 1, no matter if you're going into 2's complement or out of it. But again, they both work, so that is your personal preference. We've talked about most of these, but I want to do a quick recap of the rules when we're working with 2's complements. So when we're converting from a binary number to the 2's complement version, we need to leave the positive numbers alone. Positive numbers can be converted, but they don't need to be. They will add just fine the way they are. If you have a negative number and you need to add it, that means you need to do the 2's complement. So make sure it's in binary, unsigned binary, or signed binary, doesn't matter. Then you're going to invert and add 1. When you're converting back from a number that is in 2's complement, again, you don't have to go to or from 2's complement with positive numbers. They're fine as is. And then for negative numbers, it's the exact same process. Invert, add 1, and then if you need to, convert it back to the decimal form. Something else that's really important that I've waited to talk about until we've worked through a couple examples, because I think it'll be a little bit easier to understand now, is that when we use 2's complement, we're using that most significant bit to represent either a positive or negative number, right? So we need to make sure that we know the limits of the number we're working with. So typically we've been working with nibbles of numbers for bits, right? And when we're using 2's complement, we can only represent numbers according to these equations right here. So the largest negative number that we can represent is 2 to the power of however many bits you're using. So we're using 4 bits, right? That's what we've been using, minus 1. So we'll calculate that in a second here. And the highest positive number that you can use when you're working with 2's complement is 2 times however many places or bits you're using. So again, that's 4 minus 1 to that power, and then subtract 1 from that number. And again, n is just the number of bits that we're using. So when we're working with nibbles, that's 4 bits, using our 2's complement, for a negative number, we can represent -2 to the power of 4 minus 1. So that's going to be 2 to the power of 3, or -2 to the power of 3, which is just -8. And then the largest positive number that we can replace is 2 to the power of 4 minus 1, which is going to be 8, but then we need to subtract 1 from that. So that's going to be +7. So when we're working with 4 bits, in unsigned binary, we can represent that up to the number 15, right? But because we are reserving that most significant bit as a sign denominator or a sign designation, we only have 3 bits left to work with. And this just outlines this a little bit better here. So for the number -7, we need this 0 to indicate that it's a positive number. And then we can fill every other place up with 1s. And if you're working with a whole byte of information, right, that's 8 bits, it would be the same thing. You would have 0 as your most significant bit, and then we would just fill in all ones behind it, and that would be the largest number that you could create. And then for -8, we see that we need a 1 to designate that it's a negative number. And then it's a little counterintuitive, but to get the largest number, you fill everything after that with zeros. So this is actually the 2's complement that indicates the number -8. Working with 2's complements might seem like a lot of work to you. You might be asking, why do I even need to bother with this? Well, if you remember, we said earlier that we can't just add our typical signed binary numbers. We need a 2's complement if we are working with a negative number. So the steps for adding when you have a negative number is first, if you have decimal numbers, convert those to binary. And then any negative numbers you're going to want to convert to their 2's complement. We're going to add those numbers and then we can convert back to our regular binary. So I'll show you that here. So we have the number +5 and -5. And I'll walk you through the 2's complement for -5 real quick. So this is our +5. We'll start with unsigned binary. We'll flip everything, we invert, we add 1, and this is our -5. So this is our 2's complement number right here. So now that we have our 2's complement, we can stack these up and add them together. 1 + 1, 0, carry the 1. 1 + 1, 0, carry the 1, and so on. And then we end up with this extra bit right here. So we're working with 4 bits right now. And you need to always be mindful of that as well, how many bits that you start out working with. So this 1 all the way on the left here is an extra bit, right? We're only working with 4, and this is the 5th one. So because we've just carried it out, we get rid of it. It's outside of our limit, and that's perfectly fine. So we're left with 0, 0, 0, 0, which we find does equal, it's 0, of course. So you can see that we can correctly add numbers when we use 2's complement. So now we'll look at a couple more examples of adding negative numbers using 2's complements. So here I have the number +4 plus a -2. So we have our +4 written in binary over here and our -2 written as its 2's complement. And I will go through that real quick. So a -2, and here I'm starting out with signed binary form. So this 1 is representing a negative. So we have -2 written in signed binary. We invert everything except this 1, right, because we're starting out with signed. And you'll see as I go through some of these examples, I think I flip-flop back a little bit between using signed and unsigned binary. And again, you just have to know which one you're working with when you're converting. But you'll get the same answer whichever you're using. So we invert everything except our most significant bit. We add 1, and that's how we get our -2 in 2's complement form. So now I can add these numbers together. And I'm not going to walk through all of this, but essentially if you do all the carrying, here's what we end up with. And you'll notice we have an extra bit again all the way on the left. So we can only have 4 bits. We started out with 2 4-bit numbers. Our answer has to be 4 bits. And so this one simply just goes away, right? If you have an extra bit that exceeds your limit, it typically, and I'll explain this momentarily, but if it's what we call a carry out, it just goes away. And so we see this number here is the binary number 2. And we know +4 plus a -2 is equal to 2. So everything has worked out there. Again, that's a good way to check your addition with the decimal equivalents. So now we have the decimal numbers 6 plus a -5. And here I'm converting my -5. So I'm starting out with the signed binary number 5. My most significant bit is representing a negative, 4 plus 1. So I invert everything except this most significant bit because it's already indicating negative, so I want to keep that. I'm going to add 1. That's our number for -5, our 2's complement. So now I can add these together. And again, we have a carryout bit. We have an extra that exceeds our limit. So we get rid of that. And we can see that these are equal. So we have a 1 in binary equals the 1 in decimal that we should have ended up with. I talked about carryout bits just a second ago, and I want to elaborate on that a little bit more now. So a carryout bit is what we call when our bit limit is exceeded. So we've been working with nibbles of data, so 4 bits. And the most significant bit, of course, indicates if that number is a positive or a negative. So if we add our numbers together and we have 1 left over, because our bit limit is exceeded, we just get rid of it. It's fine, it goes away. However, there is a case called an overflow, and that's where the sign bit is incorrect. So if you add, when you're adding 2 numbers, it should always have the same amount of bits. So if we add 4 bits and 4 bits together and we end up with 5, that 5th bit should match the sign of the numbers we're adding. So if we're adding 2 positive numbers, you should not have a 1 left over. If you have a 1 left as the 5th bit, that would indicate that it's a negative number, which is incorrect. And that would be an overflow, not a carryout. Likewise, if you're adding 2 negative numbers and you end up with a positive result, then you've exceeded the number that you can possibly make. So this overflow bit indicates an incorrect result. And this is a little bit difficult to explain, but I have some examples in the next slide that should clarify this. Here are the examples, and below I've pasted in the rules. So the first thing we want to look for is an overflow, and if an overflow isn't happening, we'll know if it's a harmless carryout. So looking at this first example over here on the top left, we're adding a -39 and a 92. So the signs of the numbers are not the same. So looking at our overflow rule down here, we can only have an overflow if the signs of the 2 numbers we're adding are the same and the most significant bit is different. So we're adding 2 different signed numbers, a negative and a positive, which means this extra 1 over here isn't an overflow, it's just a carryout. It's fine, we can get rid of it. Moving on to this next example right below it, we have a positive 104 and a positive 45. So now we do need to watch for overflow here because these numbers both carry the same sign. So what we see, 1, 2, 3, 4, 5, 6, 7, 8, we have an overflow with no carryout here. And we know that because we haven't ran out of room, right? We don't have anything over here. We're still within our 8-bit limit. But the red flag here is that our most significant bit should be a 0 because we're adding 2 positive numbers, but it's not, it's a 1. And this indicates that we've ran out of room. We need more bits over here to show us that this is a positive number, but we can't, we've ran out of room. And our most significant bit that needs to indicate the sign, it just can't because we don't have any space left. 8 bits, or we can only really use 7 bits, right? And 7 bits cannot contain the positive number 149. So looking at our next example right below that, we have a positive 10 plus a -3. So we know that we don't really have to be worried about overflow, but we might have a carryout. And we do. We have this one over here. It's a carryout. That's perfectly fine. Okay, going to this next example. Now this is an interesting one because we have -19 plus -7. So we have 2 signs that are the same, so we do have to watch for overflow. And you can see here that we do have an extra 1, but there's no overflow because our most significant bit down here, right, we want to make sure we're only using 8 bits. and we are, this 8th bit indicates a negative, as it should. When you add two negatives, you should get a negative. So this most significant bit is perfectly fine, so there's no overflow, and this 1 just gets carried out, no problem. Moving on, we'll keep walking through these because I think this is a little bit of a more complicated concept, so I want to make sure we've really nailed it. We have a negative 75 plus a 59. These numbers do not have the same sign, so we don't have to worry about overflow. And we're also not exceeding 8 bits, so there is no carryout either. And the reason why you don't have to worry about an overflow when you're adding two numbers of different signs is that they're going to counteract each other a little bit, right? So you could have the maximum of a negative and the maximum of a positive, and they're going to cancel out. You're not going to get a number that you're not able to represent with that number of bits. It's just impossible. So we only have to worry about overflow if we're adding two numbers that are the same sign. So looking down here, we have 127 plus 1 is 128, and this is exactly what I'm talking about when you run out of room because of the same sign. So actually, this is a great example. 127 is this number on top. And you can see this is the maximum that we can represent with 8 bits, right? Because we need this 0 to say that it's a positive number. And we've filled the rest up with 1s. That means that when we add 1 more, we simply can't contain it in our 8-bit system and still designate it as a positive, right? We need this most significant bit to say positive or negative. So when we add these together, our most significant bit is a 1. That's saying that this is a negative number, but we know it's not because we've added two positives. So we have an overflow. This number, again, would need more zeros added to the end of it to indicate that this is a positive number, but we don't have that. We only have 8 bits, and we need one of those to represent the sign. So we have an overflow here. All right, working on this example, top right, we're adding positive 44 plus positive 49, or 45, excuse me. And we see our most significant bit is a 0, which is great. We're adding two positives, so our most significant bit should be a 0. So we don't have an overflow, and we don't have any carryout either. Looking at this next example, we have a negative 103 plus a negative 69, so we have two of the same signs, so an overflow is possible. We need to watch out for that. So when we get done with all of our addition, we're going to look at our most significant bit. Make sure you're looking at the 8th one. And we see it's a 0. And we know that our most significant bit should be a 1 to represent that this is a negative number. And we also, so we know we have overflow, we also have this 1 up here that is a carryout. So this number is not correct. And hopefully I've mentioned that before, but if I haven't, when you have overflow, that means that your sum is not correct unless you are able to add more bits. And then our last one, negative 1 plus 1, we have a carryout that is fine to get rid of because these signs are not the same, so we don't have an overflow. So I know that was a lot of examples that we just worked through illustrating overflow versus carryout, but I do want to make sure that we really grasp this concept, and it's not covered in the textbook, so I want to make sure I was really thorough there. So now that we hopefully understand the difference between carryout and overflow, I want to circle back to our addition examples so you can really understand why we got rid of numbers. So looking at this example on the left, we have a positive 4 plus a negative 2. These signs are not the same. That means we're not going to have overflow. They're going to counteract in some way so that we're not going to run out of space. So that means this extra 1 over here is just a carryout. It's perfectly legal for us to get rid of it. Same thing on the right. We have two different signs, a positive and a negative. So that means this carryout over here is perfectly fine. We can get rid of it. In all the 2's complement addition examples that we've looked at, the sum has always been a positive number. And so we've been able to easily tell what the binary number is. However, if we end up with a sum that is a negative number, we have to do a little bit of extra work to be able to understand that. So what we're going to do, just to quickly illustrate this, is we're going to add the numbers -2 plus 1. And here's this again, a quick walkthrough on conversion. And I was talking about flip-flopping back and forth between signed and unsigned to do this conversion, and you can see that here. So here I've started with an unsigned binary 2. I'm going to flip everything because it's unsigned. So flipping everything, adding 1. This is the negative, or the 2's complement for -2. So now that I have that, I can add these two numbers together. On the right, doing some quick addition, I should know that I should end up with a -1. And when I go through adding up everything binary, I end up with 1111. Okay, so what does that mean? This most significant bit is indicating that this is a negative number. So anything that's a negative number in 2's complement needs to be converted back out of 2's complements. So the positives are fine, we can leave those alone, but the negative numbers will have to convert to understand, because right now this does not look like a -1. So there's two ways we can do this. We can convert the sum to binary. So we start out with 1111. This is the 2's complement form, same number as we had down here. And we invert everything and we add 1. So just the same process of converting back. We just haven't done it with a sum yet. So if you end up with a negative sum, you need to convert back, just invert and add 1. And remember that it is a negative. Another way to do it is we can convert the sum to signed binary if we still want that most significant bit to represent the sign. Same thing, starting with 1111. We invert everything, but we leave our most significant bit. Just like when we convert to 2's complement, if we start with a signed binary number, we leave that most significant bit alone, right? So likewise, when we convert from 2's complement to signed binary, we leave that most significant bit alone. So we invert everything and then we go ahead and add 1, and this is the signed binary representation of -1. So you can do that either way, it just depends which form you want. If you want to convert to a binary form or if you want to convert to a signed binary form. I'm going to walk us through one more example here where we end up with a negative result. So here we have a +3 plus a -5. So I start out, again, quick conversion. Here's 5 written in unsigned binary. Invert everything, add 1. Now we can add +3, -5. We know we should end up with -2. And here we see our most significant bit is a 1. And so we know that we need to convert this back. This is going to be a negative number. So if we convert it to binary, I have the same number just carried over here so we can understand better. We invert everything, add 1, and we remember that it is a negative. So this is a -2, just like we should have got. If we want to convert to signed binary, here's the number that we're starting with. Again, we leave the most significant bit alone if we're converting to signed, and then we add 1. So in signed binary, this represents -2. We've been adding negative numbers to positive numbers all this time. Hopefully you remember this from algebra or algebra 2, but when we are subtracting numbers, so 5 minus 3, this is equal to 5 plus a -3. So if you need to subtract binary numbers, it's the exact same process. You're just going to add some parentheses essentially and assign the negative to a number. So instead of subtraction, you're turning it into the addition of negative numbers, and we can work through that the same way that we just did to do subtraction with our 2's complements as well. Earlier we made a big deal about overflow bits, right? So if we started with 4 bits in each of our numbers, we had to end with a sum that was 4 bits. Same in all of those examples that we walked through. We had 2 8-bit numbers. The sum needed to be equal to 8 bits or contain 8 bits. So now we're going to look at why that's so important. So typically, if you're working with positive numbers, we just copy zeros in to fill out the number. So if you were adding, if you needed to add two 8-bit numbers, and we started out with 3, right? So this is our 4-bit representation of the number 3. We could go in and just extend that most significant bit, or I'm sorry, copy zeros in. You would just fill in everything else with zeros, and we would still be representing the decimal number 3. However, here I have a 4-bit value that is the 2's complement of -5. But when I fill this in with zeros to make an 8-bit number, this looks like the number 11. My most significant bit all the way on the left is not showing me that this is a negative number anymore. This is why it's important that when we're working with signed numbers, and we know we're going to be working with signed numbers, that most significant bit is what's copied across to extend that number. So here again is our example 1, our 4-bit representation of 3. Our most significant bit is a 0, so we are going to extend that 0 to make this an 8-bit number. That's the same because this is a positive number. However, our -5 is what tripped us up before, right? So here's our -5 represented 2's complement with 4 bits. If we extend this most significant bit 4 more places to turn this into an 8-bit number, this number will still convert back to -5, or to 5 in unsigned binary. So the value is still retained, and that's why it's important when you're doing extensions of a number, when you're filling it out. Maybe we need to add this to another 8-bit number, so we need to make sure that there's the same amount of bits, that you're using the most significant bit to fill out all of those empty spaces. And it's also important to note that you're adding that bit to the left. You always want to fill out to the left. Do not fill out the number to the right, or else you will end up with the incorrect number. Now that we've had a very long conversation on 2's complement and signed binary numbers, we are going to jump into logic gates. So logic gates are binary inputs that are transformed in some manner when they're output. And we'll look at some illustrations of this in just a second. So these gates are transforming the numbers, and we use what's called truth tables to represent the numbers that are being input and the numbers that are being output. It's a list, almost like a times table list or an addition list. And with these logic gates and truth tables, we have Boolean equations. So these Boolean equations are mathematical expressions that we can write down that are describing what these logic gates are doing. Our first gate that we're going to talk about is a buffer gate. This is technically a gate, but it's pretty simple and pretty boring, to be honest, but that's good. This is a good gate to start out with. So in a buffer gate, whatever is input, the output is going to be equal to that number. So over here in my truth table, I have the number 0. So if I input a 0, I am going to get a 0 out. And you'll see these letters Y and A, they're written all over, right? So this is the gate shape, is a triangle up here. And the A is representing the input, and the Y is representing the output. So this is our logic gate diagram. And down here we have our Boolean equation. That's our mathematical equation that describes what's going on in the gate. So this equation is saying that the output is equal to the input. This is our Boolean equation. And below that we have our truth table, where we list out all of the possible inputs and outputs. So we have our 0. Now if we input a 1 into this buffer gate, logic says, following this equation, we're going to get a 1 out of it. So a pretty simple gate. We'll take a look at some more complex ones. Now we're going to look at a NOT gate. This NOT gate only has one input and one output. And this gate is just saying that the output is going to be the opposite of whatever is input. So up here we see we have our triangle again, but we have a circle in front of it this time. And this little circle is indicating the N, the NOT gate. So we have an A that's being input, a Y that is our output, and here is our Boolean equation. So our output is going to equal the inverse of our input, and this little straight line above the A just means inverse. So if we are inputting a 1, we're going to get out, if we're inputting a 0, we're going to get out the inverse of that, flip it, it's going to be a 1. That's the output. If we're putting a 1 into the gate, our output is going to be the inverse of that, so it's going to be a 0. Next, we have an AND gate. So an AND gate actually has 2 inputs. Our other gates only had 1 input. An AND gate has 2 inputs, so we represent those with an A and a B, and our output is still Y. And here, our output is only true or equal to 1 if both inputs are true or equal to 1. So when we're using gates, sometimes we'll use the terminology true and false, and that simply means true is equal to a value of 1 and false is equal to a value of 0. So we have our Boolean equation down here. Our output is just equal to A times B. That means if either one of these is 0, of course you multiply anything by 0 and the result is going to be 0. So this is our resulting equation to describe what's happening. So now if we go down to our truth table down here, we look at all the possible combinations that we could have passing through this logic gate. So our first combination is if A and B are both zeros, are both false, we would get a 0 back because we need both inputs to be true for our output to be true. So next, if A is 0 and B is 1, we're still going to get an output of 0. If A is 1 and B is 0, still going to get an output of 0. But if both A and B are true, or on, or equal to 1, whatever terminology you want to use, we will get 1, or true, or on, as our output, because these are being multiplied together, right? 1 times 1 is 1. Both inputs are true, therefore the output is true. Now we have another gate that has 2 inputs and 1 output, so we're still using A and B to describe our inputs, Y to describe our output. But this is an OR gate now that we're looking at. So an OR gate means that either A or B need to be true in order for the output to be true. So either one. It does not need to be both like the AND gate. And luckily, the types of gates, they're a little bit descriptive or indicative of what they're doing. So an AND gate, you need both A and B to be equal to 1 for an output of 1. An OR gate, you only need A or B to equal 1 to get an output of 1. So now we'll look at our truth table down here. If we have an input of 0 for both A and B, of course we will get out a 0. If A is 0 and B is 1, remember it's an OR, so only one or the other has to be true, we will get a true output. Moving on, if we have a true or a 1 input for A, nothing input for B, we're still going to get a positive true output for Y. Now, if we have both a true input for A and a true input for B, that's perfectly fine. We're still going to get 1 as our output. Now you might be looking at the Boolean equation up here and saying that Y is A plus B. Shouldn't this output be 2? No, it should not, because the only options you have are true or false, right? There's no 1, 2, 3, 4. We're just using 1s and 0s to represent true, false, or you could think of it as on or off, right? So you can't have something be doubly on, or on times 2, it's just on. So even though we have 2 1s here, both A and B are on, the output is still just 1. It's true or on. Now we have what's called an XOR gate, and this X represents the word exclusive. So here we can only have one or the other input be on for us to get a true output. So we still have 2 inputs, 1 output. but our output is only true if only one input is true. And this down here is our sign that we use in a Boolean equation to represent this. And you'll notice this diagram looks a little bit different too. So we use different shapes to represent different kinds of gates and different things going on. So this little space here is what's representing that exclusivity of the gate. So in our previous example, the OR gate looks kind of like this odd shape here. This time we've added a little, another line in front of it to represent that it's exclusive. Okay, so we've got the diagram, we've talked about the Boolean equation, let's look at our truth table. So remember, one or the other have to be true to get a true output. So of course, if we input 0 as into both A and B, we're not going to get anything out, it's going to be false. If only B is true, we're going to get a true output. If only A is true, we're going to get a true output. But because this is an exclusive OR gate, that means it can only be one or the other. If both A and B are true, we're going to get a false output. Next, we have a NAND gate, and NAND just represents not and. So whenever we have not in the diagram, we'll see this little circle in front. You'll remember our NOT gate before was the inverse of whatever was being put in, and that works the same way here. So our NAND gate is actually the inverse or the opposite of our AND gate. And I brought this AND gate back to remind us of the outputs there. So our AND gate, we only get a true if both inputs are true. The NAND gate is the opposite. We get a true unless both inputs are true. So working through our truth table, we have both inputs are 0 or false, so our output is going to be true. In our next one, only B is true. That's fine. Our output is still true. Same thing, when A is the only one that's true, our output is true. Now remember, it's the opposite or the inverse. So in a NAND gate, when both inputs are true, our output is going to be false. So we can see here that our NAND gate outputs are the exact opposite of our AND gate outputs. And so next we have a NOR gate. So this is a not OR gate, and hopefully you recognize that a NOR gate is the function of an OR gate, but the opposite outputs essentially. So here we see our little circle again representing the not, and we have two inputs. So in a typical OR gate, the output is true if one or both inputs is true. Here we have, in a NOR gate, our output is only true if neither input is true. So I'll bring up our OR gate down here as a reminder of how it functions. And we'll go through our NOR gate truth table. So when we have both inputs are 0, our output is going to be 1. If B is the only one that's true, we're going to get an output of 0, right? Because that's the opposite of what's happening on an OR gate. If A is the only one that's true, we're going to get a 0 output as well. And if both inputs are true, we're going to get a 0. So remember, whenever you have this not going on in your gate, whenever there's an N in front, it's just going to be the inverse of whatever that original gate is. So now we're going to get a little bit more complicated with our gates. We've had an OR gate, we've had a NOR gate, we've had an XOR gate. Now we're going to combine all of those into an XNOR gate. And so again, N is just the complement or the opposite of an exclusive OR gate. So it's the complement of an exclusive OR gate. We have two inputs here, one output. So let me bring up the XOR gate just as a reminder. So an exclusive OR gate, again, only one or the other input can be true for the output to be true. So this is going to be the complement to that exclusive gate. So here we have two zeros. Both of our inputs are false, which means we're going to get an output of 1. Our output is true only if the number of true inputs are not equal to 1. So here we see that scenario happening right here. We have one input that is true, so we're going to get a false or a 0 output. Same thing, but this time it's our A input instead of B. We're going to get a false output. And here at the end we have 2 true outputs. So we're going to get, we had 2 true inputs, so we're going to get a true output. So you can see here, looking down this list, that the N is indicating it's not, or it's the complement of an XOR gate. And we can see that the results that we have are the inverse of a typical XOR gate. So if you have trouble figuring out what the truth table should be, what the output should be for a logic gate, I would recommend trying to take a step back. So instead of trying to factor in all of these things, maybe take away the N and say, okay, if I just have an XOR gate, an exclusive OR gate, what will my outputs be? Okay, now I know the N is the inverse, so let me just inverse all of those. And that'll help with your understanding of how the gates work and with coming up with the right outputs. All of the logic gates that we've looked at up until this point have only had 1 or 2 inputs. That is not something that has to happen. These logic gates can have as many inputs essentially as you want, and the logic applies across all of the gates. So we'll take a closer look now at a NOT OR gate with 3 inputs, and we'll look at an AND gate that has 4 inputs. We'll look at the AND gate first because I think it's a little bit easier to understand. And you'll notice that when we have 4 inputs, our truth table gets a lot larger. So our truth table needs to account for all the possible combinations of the inputs. And when we have more inputs, we end up with a lot more possible combinations. However, the AND gate is still pretty straightforward. It still does the exact same thing. You'll remember that it multiplies all of the inputs. This is our Boolean equation. And the output of an AND gate is only true if all the inputs are true. So A and B and C and D all have to be true for the output to be true. So in filling in our truth table, all these possible permutations, the only time we are going to get a true output is if everything is true, and that's this case down at the bottom. All other combinations are going to get a false or an output of 0. Now we're looking at a NOR gate or a NOT OR gate with 3 inputs. You can see our little NOT symbol here in the front again. And so a typical OR gate, right, any combination of true values will equal a true output. So we just need at least one input to be true to get a true output. Well, remember when we add the NOT, that flips that logic. So what this means is that the output is only true if no inputs are true. And so that makes our truth table pretty easy for these. We see in our first row here, none of our inputs are true, so our output is true. And for the rest of the permutations, we have at least one output being true. And so this being a NOT OR gate, that means that the outputs are all going to be 0. They're all going to be false because there is always an input of some kind in all of these other combinations. We've looked at all of these logic gates, and I think it's easy to see how binary numbers or true and false indicators tie into those, but how do these tie into the real world? Why do we need logic gates? We'll just strip it down to some very basic examples. We're going to look at when we would want to control an output based on the inputs. So the first example here is a burglar alarm. And this would be, we have the symbol for an AND gate here. And hopefully you'll start to recognize some of these symbols. So this is a symbol for an AND gate, and that means both inputs need to be true for the output to be true. So looking at these inputs, instead of giving them 1s and 0s, we will assign them a name. So our first input would be a person sensor, which is kind of an odd name to give this, but if you had a person sensor, or maybe we say a motion detector in your home, and it registered some motion, that would be an input of 1, right? That would be an active input to the alarm. If you had an alarm switch as well, if your alarm was turned on, you would need your alarm to be turned on, right? And so you would probably turn your alarm on if you were leaving your home. That's what would activate your alarm. So if your alarm switch was on, saying, yes, I'm away, please be active, that would also be an input of 1. And we know for an AND gate, we need 2 inputs, or all the inputs, rather, have to be true for our output to be true. So if you're away from home, you set your alarm switch on to be active. Your motion sensor is sensing somebody moving around. That's going to set off your burglar alarm. So this is a very real life case of where we would be using a logic gate. Essentially, an AND gate is being performed to trip the burglar alarm. So in this next case, we're going to consider a doorbell, and we'll say that you have a front doorbell and a back doorbell. Now, thinking about what kind of gate we would use here, what kind of logic would we want to use to make the doorbell ring? And the clue is in this little text down here. If you read it, if either the front doorbell switch rings, or the front doorbell switch is pressed, or the back doorbell switch is pressed, we want it to ring, right? So this would use an OR gate as its logic gate. So if either the front doorbell switch rang and had an input of 1, or if the back doorbell switch rang and had an input of 1, the doorbell would go off. Or if you managed to press both simultaneously, the doorbell would still go off. And here in this last application, we have a NOT gate, and we're considering a temperature detector. That's going to be our input. And the temperature detector is looking for a temperature that's above 20 degrees Celsius, which is about 70 degrees Fahrenheit. And then we have our central heating system, which turns on or off based on the input of the temperature detector. So if the temperature is above 200 degrees, is above 20 degrees Celsius, then we would have an input of 1. And our NOT gate is going to flip that so that our central heating is turned off. So if we're getting above 70 degrees, that's too warm, we're turning the heating off. If our temperature detector senses a temperature below 20 degrees Celsius, it's going to give an input of 0, right? It's not going to register anything. And our heating system is going to flip that input with our NOT gate, and the central heating system will be turned on. So this is another practical application of a logic gate. We've covered 2 of our major topics now, talking about adding binary numbers and talking about logic gates. We are on to the last one, architecture comparison. So last week, we very briefly touched on the difference between microprocessors and microcontrollers. So now we're going to take a look, a more detailed look at the difference in the architecture between them. And this illustration, I believe, is in your textbook. It illustrates some of the internal components of these. So we see at the top a microprocessor. Grab my little highlighter. A microprocessor typically has these main components. It has a CPU, an ALU, registers, and it's communicating via these buses. Whereas a microcontroller, we can easily see it has a lot more components in it. Like the microprocessor, it has a CPU, the ALU, the registers, but a microcontroller, if you'll remember, is more of a standalone unit. It does not have to depend on anything else to function. It also contains counters, timers, RAM, ROM, and I/O ports, or input-output ports. So it contains a lot more components, and it also communicates via buses. So what do all these terms mean? Let's move on and we'll see the explanation for some of these terms and what these components are actually doing within microprocessors and microcontrollers. So based on this example, we have these components here. Please take a second and determine if you think this is a microprocessor or a microcontroller. We have a CPU. We don't see the ALU, but it's here, right? We have input ports, output ports, RAM, ROM, and a clock generator. And because we have all of these components, that means that this is going to be a microprocessor. Okay, and for this one, we are just looking at what is in this isolated box right here, where we have an ALU, the control, or maybe the CPU and the registers. So this has a lot more limited components, right? It has all the main components of a microprocessor and none of the extra ones that we would find in a microcontroller. So if we considered the system as a whole, this could be a microcontroller. Maybe if we added a clock in here, we would have all the components for a microcontroller. But this initial box right here that we first considered would just be a microprocessor based on its architecture. So you may have noticed that we have registers in both microprocessors and microcontrollers. But what is a register? So a register acts as a temporary storage location. These locations all have an address and they all store data. So think of a register much like a mailbox, right? Every house or every address usually has a mailbox, and the mailbox holds data, or rather mail, right? That contains data. So registers are just places that data is stored, and each one has an address so that we know where to pull that information from. So a very simple, what we would call a register file is a set of registers with a decoder. So the register file is using these addresses and it is using them to store the data that is being input. So if you're storing a binary number, that would be input into a register. And if we needed to read that number, it would be read with a decoder that is pulling the data out of that address, out of that register address, and it is reading it. The issue here is we don't always want to input data. Sometimes we need to read it too, and that's where the decoder comes into play. And sometimes we need to read two values at one time. So you can see in this illustration, in our register file, we have an address and we have one line for data coming out. But sometimes we need to read two values at once and we need to add a value back into the register. For example, if you're pulling a number from register 1, you're pulling a number from register 2, you need to add those together and store the result back in register 1. How do we do that? And this here illustrates what I've just explained. I got a little bit ahead of myself, but this kind of shows you that in our register file, we can add different address ports, and we can also add multiple places for data to come out, or multiple ways to process that data. And what we can also do is add a third address port so that we can temporarily store the address of our data. So we can store the data in registers and we can pull the data from registers, but how are we processing it? All of this data that we're talking about is getting processed by the ALU. And we've talked about that a little bit earlier, just the ALU as a component. And now we can see what it actually does and what it stands for. So ALU stands for Arithmetic Logic Unit, arithmetic meaning math. And it's doing math comparisons like our logic gates and other operations. It's performing all of these calculations with that information that we have, or it's comparing the data. It's manipulating the information that is in the registers. So the ALU is doing all of the calculations, but it needs something to tell it how to do the calculations and what calculations to perform. And these instructions are coming from the CPU. CPU stands for the Central Processing Unit. And this is what is essentially controlling everything, and it's what impacts the overall computing power of a system. So if you need your system to perform a lot of tasks or do really complex things, you'll need a much more complex CPU or a much higher grade CPU for that. And it's what manages most of the operations that are happening. So you can think of the CPU much like the manager of a department at work. So the CPU might not be doing a lot of work or any work itself, but the CPU is what's giving out instructions for everything else to work together. It's what's telling the ALU to pull from the registers. It's telling it how to process that information from the registers. It's telling you what things need to go back and forth on the buses. This is where all the processing power is coming from. So I just mentioned buses. What does that mean? We can see in the diagram that we have three kinds of buses listed for the microprocessor and for the microcontroller. And these buses are all doing different things. So in short, buses are responsible for the communication, the back and forth that's happening in these processing units. Much like in real life, a bus is what's responsible for transporting people back and forth. These buses are moving information of some kind. So we have three different main kinds of buses. The first is the address bus, and it's what's transferring the addresses of the memory, the registers, or the input and output devices. So each register or input output, anything connected to the system has an address, and these addresses are essentially stored separately and communicated back and forth by the address buses. Now at each address, there's some data that's being transferred, right? We're pulling or we are storing some kind of information, and that's done separately with a data bus. So we keep these separate. One bus handles the addresses, one bus handles the data. And what we usually have is bidirectional data buses, or I'm sorry, what we always have is bidirectional data buses. And that means these buses go back and forth. They can pull information and they can also deposit information. Lastly, we have the control bus, and this especially works hand in hand with the CPU. So the control bus is what is carrying all the information, or I'm sorry, the instructions. The control bus is carrying the instructions back and forth, the read and write instructions, any timing instructions. So the CPU is oftentimes communicating using the control bus. So we have the control bus with the instructions. The address bus is in charge of the addresses, and the data bus is responsible for the transmission of data. Next, we're going to take a look at counters and timers. So previously, everything we looked at, the registers, the ALU, CPU, and buses, those have been components that are on both a microprocessor and a microcontroller. Now we're going to start taking a look at components or pieces that are unique to microcontrollers. They're part of a more complete system. So microcontrollers will have a counter and or a timer in them. And counters are essentially counting up and down, working in binary. And they can add things, or timings rather, that they're counting, or they can reset the count. And timers are doing a similar task. So timers are gathering information on the speed of the system, and they are storing this the system speed information in a register. So we need counters and timers to monitor different things in our system. And they're just counting and timing and storing this information in the registers. It's available to pull from as needed. Next, we have the I/O ports, or the inputs and the output ports. And some ports can be uniquely inputs, some can be uniquely outputs, some can be both. And I'm going to keep this discussion very broad for these components because this can be such a variety of things. So any inputs or output ports are connecting the system to an outside source, or they're connecting the system to something else that's external. So for example, a keyboard is an input source. If we connected a keyboard, think of it connected to your computer or connecting a keyboard to a microcontroller. When you are pressing those keys, you are providing an input to the system. And likewise, if you have a screen connected to your system, the display on that screen is an output. That screen is reflecting whatever the system is outputting to that screen. So there's a lot of different examples here. There's a lot of potential inputs and outputs for systems, but just know it's essentially anything that is allowing the system to communicate with the outside world. These systems that we've looked at have registers to temporarily store information, but it's important to note that registers are not a good place to store information long term. So they're good for performing calculations, temporarily storing the answer, but if you need to store data for a long period of time, we use memory. It's great for large amounts of data. We can still use addresses to retrieve or store the data, and there are a lot of different types of memory, so we'll get into those. The First two memory types that we're going to take a look at are RAM and ROM. You've probably heard of these before. They used to be very common. So RAM stands for random access memory, and what that means is that a random address is accessed at the same speed as any other. So there are no data addresses that can be accessed faster than others. Think of it as you could go to any house on the block at the exact same speed. It wouldn't take you longer to go 2 blocks down versus 1 block down, which is an impossible example, of course, in our world, but that is how random access memory works. Everything is accessed at the same speed. What's also important to remember with RAM is that it's volatile. So what that means is if you turn the power off, the memory is wiped clean. Whereas with ROM, read-only memory, it is non-volatile. So if you turn off a system with ROM, and when you turn it back on, the data stored in the memory will still be there. And just like RAM, all of the data addresses are accessed at the same speed. And ROM used to be read-only, but now you can actually read and write to ROM. So the capabilities have changed, but its name is still indicative of how it functioned in the past as read-only. And what that means is you could only pull data from the ROM. You couldn't store anything there. You could just retrieve data that was already set. The next two closely related memory types are DRAM and SRAM. So DRAM is dynamic random access memory. And what it does is it stores a bit or the information as the presence or absence of a charge in a tiny capacitor. So the capacitor stores the charge. However, if you're familiar with capacitors, when you remove the power source or the source of the charge, it will slowly die away from the capacitor. So if you stored information in a dynamic random access memory, you would have to periodically power it up and provide it power for those tiny capacitors to maintain their presence of charge. Otherwise, the charge would slowly die away and you would lose anything stored in that memory. Whereas in SRAM, static random access memory, the bit is stored as the presence or absence of charge using cross-coupled inverters. So what these inverters do is they keep each other charged. So even if there's no charge or no power to the system, the charge is maintained, and therefore anything that is stored in this memory is maintained. So all of these memory types that we've talked about have had ROM or RAM in their name, and that's indicating that most of these, or all of these that we previously talked about, have been read-only. So what that means is they can be programmed once, and then not again. So once you input data into that memory system, you can only retrieve that information. You can't store new information. So that being said, we're going to take a look at 3 more different kinds of memory types. And the first one is PROM, Programmable Read-Only Memory. And this name is pretty self-explanatory. So the programming can only be done once, because it's done by blowing fuses. So once you blow those fuses, you can't go back. So whatever you program better be right the first time, because you cannot change it. And then we have EEPROM. So EEPROM is erasable programmable read-only memory. This is programmable, or reprogrammable rather, because it uses different components. However, you can't just reprogram it with anything. You have to erase the existing data with ultraviolet light before you can reprogram it. What is a lot more user-friendly and easier to use is EEPROM, electrically erasable programmable read-only memory. That's a mouthful. So this can be programmed multiple times, and it uses different components to program it than the previous two. So this type of memory can be erased with built-in circuitry, which essentially means you can erase the information and reprogram it an unlimited number of times. And the last type of memory that we're going to discuss is flash memory. So we talked about how EEPROM was a lot more user-friendly. You can erase it with the circuitry that's built into the system and reprogram. But flash memory is even better. So as we've gone through each memory type, each one has been an improvement upon the last. So flash memory is by far the most used and the most advanced one that we've discussed. So what this does, the difference here from EEPROM is that flash memory erases larger blocks of bits. So it's able to function a lot faster and it is much more affordable. And flash memory was developed by Fujio Masuoka. He developed memories and high-speed circuits at Toshiba from 1971 to 1994. So he was able to develop this flash memory type, and it's called flash memory because the process happened so fast it reminded him of the flash of a camera. And what you'll be doing for part of your homework this week is actually learning more about flash memory on your own. I really like to encourage independent research and exploration in this course. So you'll be learning more about flash memory and its founder. Fujio is still alive. He is currently 77 years old. And hopefully you'll be able to research and learn a little bit more about the beginnings of flash memory. So there's recommended reading for this week. If you happen to have the textbook, chapter 1, pages 14 to 22, that will go over the signed and unsigned binary, two's complement, binary addition, all of that, as well as logic gates. And then chapter 5, pages 260 to 261, will give you a good review and a more in-depth view of the microcontroller and microprocessor architectural components.